Hello and welcome to this revision session on energy, which is a topic in paper 1 in GCSE separate science physics. So in today's revision session we're going to look at how you can answer examination questions on the topic of energy for GCSE physics paper 1. So if we've been successful and we've learned in today's lesson, we should be able to answer GCSE physics examination style questions. We should be able to assess our own understanding on this topic of GCSE physics and finally understand what areas of this topic we need to improve upon for GCSE physics. So what preparation can you do for this revision session? So when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this particular section what I would think you should be doing is writing down your working out to the questions and the answers from the questions in this revision session. And when you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst on the right hand side section, write down any pieces of information which you find useful or any hints and tips on answering the questions from this revision session. And after the end of the revision session, write up these notes into a revision sheet for you to use independently. So let's have a look at some questions in this revision session focusing on the topic of energy. So the first question says, after accelerating, the car travels along the road at a constant speed of 120 seconds. The power of the car engine is 78,000 watts. Calculate the total energy transferred by the engine while the car is travelling at a constant speed. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this particular question, you need to be able to use the equation that power is equal to energy over time. Now, for the 2022 examination, you will be given this particular equation. Okay, now, so what you should be doing in the first step of any mathematical question in GCSE physics is you literally substitute the numbers directly from the question into the equation. This shows the examiner that you are aware of where the values come from in this particular question. So because power equals energy over time, we do 78,000 equals energy over 120. The second step would then involve rearranging the equation to make energy the subject, so 78,000 times 120, so it equals 9,360,000 joules. The next question says, a car accelerates on a flat, straight road. Describe the energy transfers when the car is accelerating. So pause the video now, then unpause the video when you want to go through your answer. Right, so with this particular question, you've always got to consider three things when you talk about energy transfers. Firstly, what is the energy store that you're starting with in this energy transfer? Secondly, what's this energy store which you're going to finish with in this energy transfer? And then thirdly, is there any energy dissipated to the surroundings? So what do you start with? Well, because the car is moving, we would say that it's starting with kinetic energy, and you could also argue that it's also starting with chemical potential energy of the fuel. So you would say that the kinetic energy of the car increases because it's getting faster and faster. The chemical potential energy store of the fuel decreases because the kinetic energy store is increasing, and that there's thermal energy dissipated to the internal energy of the surroundings or the engine, car and tyres. The next question has a student investigating the effect of the starting temperature of hot water on the rate at which it cooled. So table 1 shows these results and figure 1 shows the equipment used. So the first question says, describe a method which we could use to carry out investigation safely and obtain the results in table 1. So pause the video now, then unpause the video when you want to go through your answer. Right, when you're doing these types of questions, it's always important that you consider the following things. Step 1, what is your step-by-step guide of how you would do this experiment correctly? Secondly, what measurements are you going to take and with what devices are you going to take them? Thirdly, what are you going to control to get valid results? And finally, because it states it quite clearly in the question, what safety features are you going to incorporate into your investigation to get accurate and safe results? Now, it's important that for each of these particular steps, you separate them out into different paragraphs in your answer. So what you would say is the as follows. For your measurements, you're going to use a timer to measure the time, and you're going to use the thermometer to measure the temperature, because we're seeing how the temperature changes with time. So you will record the starting temperature with the thermometer. You then record the temperature after every 5 minutes with the thermometer, and what you would then do is you would measure the time elapsed with the stop clock. Now, what have you got to control in this investigation to get accurate results? Well, you want to ensure and valid results. So you want to have the same volume of water. You want to have, maybe 200 mils of water. Make sure you have the same surface area for your beaker, and the beaker is made of the same material. Now, what are your safety features in this investigation? Well, you've always got to identify what is the issue, and then what you're going to do to alleviate that, to ensure it doesn't cause damage to the experimenter. So we've got the idea of hot water. Now, what's the risk of hot water? Okay, well, the risk that it might burn you. So what you would want to do is handle the beaker with care. Another issue is, what if the glass beaker breaks? Well, you would then say that it could possibly cut you. So again, handle that beaker with care. The next question says, from looking at the results, what was the resolution of the thermometer used in the investigation? Then next, explain one conclusion the student could make from the results given in table 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so you can always determine the resolution of the thermometer or any measuring device used in the investigation by looking at the last decimal place in which the quantity is measured to in the table. Now, you'll notice that it's not measured to any actual decimal places, so we're looking at just a whole number. And then secondly, you can see how the difference would be between the numbers given. So you can see that the difference could be 1 degrees, because you can go from 37 to 38 to 39 to 40 to 41, 42, 43, 44, 45, so on, so on, so on. So the resolution is the smallest interval between values on your measuring device. So the thermometer in this case is going to be 1 degree Celsius. Now, what conclusion can you make? Well, one conclusion could be, the greater the starting temperature, the greater the temperature change. And then you can say that the rate of cooling increases with the starting temperature. Always try and link the starting temperature and the temperature change. The next question says, the student repeated the investigation using a metal beaker of the same shape and the same size, but painted it silver. Explain why the temperature after 5 minutes was higher than with the matte black beaker for each starting temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, so how can you answer this particular question? Well, it's important to understand how matte black and silver shiny link to emission, okay, for any particular object. So what you would say is as follows. You know for a fact that silver shiny surfaces are poor emitters of infrared radiation, or you could say good reflectors of infrared radiation, whilst matte black surfaces are good absorbers and good emitters of infrared radiation. So because the silver shiny surface will emit less radiation, you would say that less energy is going to be emitted from the metal beaker, so therefore the rate of energy transfer is reduced. Our next question says, a student investigated how the mass lifted by a motor affected the efficiency of the motor. Figure 8 shows how the apparatus was used. Now, this was a method used. Add the mass to the string, switch on the power supply so that the motor lifts the mass through a height of 1.2 meters. Record the electrical energy transferred from the joule meter. Repeat steps 1 to 3 with different masses. So table 4 shows these results. So when the motor lifted a 0.050 kilogram mass, the energy transferred to the motor was 4.4 joules. Calculate X, the percentage efficiency of the motor when it lifted this mass through 1.2 meters. So pause the video now, then unpause the video when you want to go through your answer. Right, well, one of the major hints that they give you in this question is they give you the gravitational field strength. Now, also you're noting that the motor is lifting the mass. So that can tell you, both those facts tell you that the energy store that's increasing in this investigation is the gravitational potential energy. So what you want to do is use the equation for gravitational potential energy, which is energy is equal to mass times by gravity times by height. Now we know what our energy is going to be, because we know that it's 4.4. Okay, now that's in total. So what we can do is we can work out the gravitational potential energy, and then we can use that to work out the efficiency by comparing it to the total energy transferred to the motor, which is 4.4 joules. So we can work out the gravitational potential energy by doing mass times by gravity times by height. Mass and height were given in the question, so we get 0.59 joules. The efficiency is therefore the useful out, which in this case is the gravitational potential energy, because that is what you want. You want to work out the amount of gravitational potential energy, because that's the useful, because you're moving the mass upwards. Okay, and then secondly, okay, what you want to do is then divide that by the total supplied, which is 4.4. Then you times by 100 and you get 13%, or if you don't times by 100, you get 0.31. The next question says the motor wastes energy as it lifts the mass. So what happens to this waste energy? Secondly, the student continued to increase the mass on the string until the motor could not lift the mass. Explain what happens to the efficiency of the motor when it can no longer lift the mass. So pause the video now, then unpause the video when you want to go through your answer. Right, so firstly, you've always got to be aware of where dissipated or waste energy goes when you're carrying out an energy transfer. Now, in most situations, the safest bet to say is that energy is transferred or dissipated to the internal energy of the surroundings. Now, second question asks what happens to the efficiency of the motor when it can no longer lift the mass. Well, efficiency is useful energy out over the total energy in. Now, the important thing to note is if the motor can no longer lift the mass, well, if it can't lift it, it's not carrying out any useful energy, or transferring any useful energy. So when the motor cannot lift the mass, the efficiency is 0 because there's no useful output energy. It's an important thing to note that when a device breaks and no longer works, its efficiency drops to 0. Now, for this investigation, explain how the student could use the motor to lower the mass to the floor before each measurement. So pause the video now, then unpause the video when you want to go through your answer. Right, well, this question is actually a bit of a synoptic question with electricity, because you've noticed it's an electrical motor. So therefore, what we need to do is we need to ensure that the motor is moving in the opposite direction. So how can you ensure the motor turns in the opposite direction to move the string in the opposite direction? Well, you would reverse the current or the potential difference in the circuit, and that will make the motor spin in the opposite direction. The next question says figure 7 shows a theme park ride. 2 strong elastic cords are attached to towers and are stretched so that the cage is on the ground. Passengers are fastened into the cage. The cage is released and moves upwards at a high velocity. So firstly, describe the energy transformations from when the cage is released until it reaches its maximum height above the ground. So pause the video now, then unpause the video when you want to go through your answer. Right, as mentioned previously, what you want to do is you want to talk about the energy stores at the start of the transformation and the energy stores at the end of the transformation, and also if there's any energy dissipated to the surroundings. So the first mark is saying that when the cage is released, the elastic potential energy store goes down because it starts off stretched, and then after you release it, the wire is no longer stretched, so there's no longer a store of elastic potential energy, so that one decreases. Now, the second thing to note is that the cage is now moving, so therefore it indicates to you that the kinetic energy store is increasing. However, it then will decrease because it will then slow down as it moves upwards. Now, the third thing is that the actual device is moving upwards, so that's going to also increase its gravitational potential energy. Now, you can also say for another mark that some energy is dissipated to the internal energy of the surroundings. Now, the next question for this particular situation is that it says the maximum velocity of the cage is 150 kilometers per hour. The mass of the cage and the passengers is 390 kilograms. The gravitational field strength is 9.8 newtons per kilogram. Calculate the maximum height the cage reaches above the ground. So pause the video now, then unpause the video when you want to go through your answer. Now this question is actually a very challenging question, because what it's actually wanted you to work out is as follows. It wants you to understand that the kinetic energy that the cage starts with transfers into gravitational potential energy, because it starts off moving upwards, it then slows down as it moves upwards, so that kinetic energy is going to turn into gravitational potential energy. So we can say that a half mv squared is equal to mgh. So you can then substitute the values in and work out your value for h. However, there is another thing you've got to notice, and that is that for velocity we don't use kilometers per hour. So what we've got to do is we've got to convert kilometers per hour into meters per second. So to turn kilometers into meters, we times by 1,000, because k means 1,000, and then to turn hours into seconds, what we would do is we would times by 3,600, because there are 3,600 seconds in an hour. However, because it's per hour and therefore per second, we would actually divide the value by 3,600. So our initial velocity, if you times by 1,000 and then divide by 3,600, is going to equal 41.7. So we can say a half mv squared is equal to mgh. So you substitute all your values into your equation. A half times by 390 times by 41.7 squared equals 9.8 times by 390 times by h. We work it through, we rearrange to find out h, and we get 88.7 meters. The next question says, Figure 8 shows part of a solar power station. Infrared radiation is reflected by mirrors onto tubes containing fluid. Energy is transferred through the tubes to heat the fluid. The heated fluid stores the energy so that the electricity can be generated at night. The fluid is stored at 290 degrees Celsius and then heated to a temperature of 550 degrees Celsius. The fluid needs to store 1.2 times 10 to the 13 joules of energy. The fluid has a specific heat capacity of 1,530 joules per kilogram degree Celsius. Calculate the mass of fluid needed to store 1.2 times 10 to the 13 joules of energy. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question you've got to remember the equation when we're using specific heat capacity, and that is E, the change in energy, is equal to M times by C, the specific heat capacity, times by triangle T, the change in temperature. So the change in temperature firstly is 260 degrees Celsius, because 550 minus 290 is equal to 260 degrees Celsius. So we can therefore say, substituting the values in, 1.2 times by 10 to the 13 equals M times by 1,530 times by 260. We can then rearrange the equation and make M the subject, and then we could work it through to be 3 times 10 to the 7 kilograms. The next question says, the system is 70% efficient and can supply energy for 8 hours during the night. Calculate the power output from the solar power station during the night. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, there's lots of things you've got to remember here, and that is firstly that power is equal, okay, to energy divided by time. Now, it's important to note that it's therefore going to be, okay, the time is not 8 hours, it's in fact 28,800 seconds, because we don't work in hours in physics, we work in seconds. So we've got to convert our time into seconds by times it by 8 by 3,600, because there are 8 hours and in each hour there are 3,600 seconds. We can then say power is equal to energy over time. So take our energy from the previous question, we divide it by 28,800 and we get a power of 4.1 times 10 to the 8 watts. But that's the total power supplied to the actual panel. Now we know that the efficiency is 70% or 0.7, so we want to use the equation efficiency is equal to useful power out over total power in. So we know that the efficiency is 0.7. So when we use this equation we can't use percentages, we've got to use the fraction. So 70% becomes 0.7, or the decimal, sorry, not the fraction. So we then say 0.7 equals the useful output power over 4.1 times 10 to the 8. We then rearrange it to make output power the subject, and we get 2.9 times 10 to the 8 watts. The next question says a computer component transfers 89 joules of energy to a copper heat sink. The mass of the copper heat sink is 5 grams. The starting temperature of the copper heat sink is 20 degrees Celsius. The specific heat capacity of copper is 386 joules per kilogram degrees Celsius. Calculate the final temperature of the copper heat sink. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, there's a lot of things to do before we can work out our final answer. Now, because we're using specific heat capacity, our equation is E, the energy, is equal to mass times by specific heat capacity times by the change in temperature. Now, we want to work out the final temperature, so the change in temperature is the wanted thing. So what we'll do is we'll got the energy, we'll then pop in the mass, we'll pop in the heat capacity, and we'll work out the change in temperature. But you're given the mass in grams. So the next thing you've got to do is we don't work in grams in physics, we work in kilograms. So you're going to turn 5 grams into kilograms. So 5 grams becomes 0.0050 kilograms, and you substitute it in. So we get 89 is equal to 0.0050 times by 386 times by the change in temperature. We then make change in temperature the subject of our equation, we rearrange, and we get our answer to be 46 degrees. But that's not our answer because the question asks for the final temperature. So if you notice in the question, it starts at 20 degrees, it's being heated up and having an increase in temperature of 46 degrees. So the final temperature is going to be 66 degrees. The next question says figure 1 shows a steam engine pulling a train. One type of steam engine burns coal as the fuel source. The energy from the coal is used to accelerate a train. So describe how the energy stores of the coal and the train change as the train accelerates. So pause the video now, then unpause the video when you want to go through your answer. Right, so like we mentioned before, when we're talking about energy transfers, we need to talk about firstly what the starting energy store is, what the final energy store is, and if there's any energy dissipated to the surroundings. So the first thing to note is it mentions that it's burning coal as a fuel source. So we're starting off with chemical energy. So we say the chemical energy of the coal store decreases, but then the kinetic energy of the train increases because the train is accelerating, so it's moving faster. Now that's your 2 marks, because there's only a 2-mark question, but you could also mention that some energy in this situation will be dissipated to the surroundings. The next question says a steam engine has a power output of 8,000 watts. Calculate the energy output of the steam engine in 3,600 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so when we're doing this question, it's very important that we understand that we're using our equation, power is equal to energy over time. So we substitute our values in straight away. So we say 8,000 is equal to E over 3,600. We then rearrange and make E the subject. So we say 8,000 times by 3,600 is equal to energy. So therefore it's 28,800,000 joules. The next question says, figure 1 shows a steam engine pulling the train. In the 18th century, the power output of the steam engine was measured in a unit called horsepower. Suggests why the unit of horsepower was used. So pause the video now, then unpause the video when you want to go through your answer. Right, now this isn't a standard normal question we get on an exam. It's something we've got to apply an understanding of how science works. And it's important that when we use different units in physics that aren't standard, so for example, if we were using miles per hour instead of meters per second, it's because we use it as a comparative tool, because people understand those particular units that we're using. So in this situation, what's it allowing an understanding of? It's allowing to compare the power of the steam engine to the power of the horse, because it's called horsepower, because in the 18th century people understood the typical power of a horse, so could compare it to a train very easily. Remember, if we don't use standard units in physics, they're there because we need to be able to have an understanding quite clearly of what that value actually means and what it compares to. The next question says, a rubber band was extended by 10 centimeters. The rubber band behaves like a spring with a spring constant of 36 newtons per meter. Calculate the elastic potential energy stored by the rubber band. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, once again, you look on your equation sheet and work out your equation for your elastic potential energy. Now, to work out your elastic potential energy, it's equal to a half times by spring constant times by the extension squared. Now, you've got the spring constant in this question and you've got the extension. But the trick here is they've given you the extension in centimetres. Now, we do not work in centimetres in physics. We work in metres. So you've got to convert centimetres into meters. So 10 centimeters becomes 0.1 meter. You then substitute this into the equation first. So do a half times by 36 times by 0.1 squared, and it's only the extension that is squared, not the entire equation. So make sure your brackets represent that in your calculator, and you get an answer of 0.18 joules. The next question says the kinetic energy of air passing a wind turbine blades each second is 73.9 megajoules. The mass of air passing through the wind turbine blades each second is 236,000 kilograms. Calculate the speed of air passing the wind turbine. So pause the video now, then unpause the video when you want to go through your answer. Right, so when you're answering this question, it's important that what you do is we understand we've been given kinetic energy, so we want to use the kinetic energy equation and then use this to work out V, okay, which is the velocity which links into the speed, okay, in that particular equation. So now the other thing to note is we're given kinetic energy in megajoules. Now we do not use megajoules in physics, we use joules, so we've got to convert mega into just normal values. Now mega means million or times 10 to the 6, so 73.9 is megajoules is 73.9 times 10 to the 6 joules. So that's the first thing that we do. The next thing that we do is then we pop that into our equation and say 900 million. So let's get this right, sorry, 73,900,000, sorry about that, is equal to a half times by 236,000 times by V squared. What we can then do is make V squared the subject, and we then work it out as shown on the screen to get V squared to equal 626. Then to work out V, we'll square root that value, so we square root it and we get 25 meters per second. So with that, that's the last question in our revision session. So I hope you've been successful and you've learned in today's revision session, where we should be able to answer GCSE examination style questions on energy. We should be able to assess our own understanding on GCSE physics for the energy topic, and then understand what areas of the energy topic you need to improve upon for your GCSE physics examination. So thank you very much for watching this revision session on the paper 1 topic of energy for GCSE separate science physics. Thank you very much for watching and have a lovely day.